Warm greetings, everyone. Please accept my gratitude, the European Structural Integrity Society and TC3 Technical Committee. My presentation is on a decadal review of various modeling and analysis of cracked rotors, authored by Nabam Teyi and Sandeep Singh from Northeastern Regional Institute of Science and Technology, India. I am Nabam Teyi. This work falls under the domain of rotor dynamics. A rotor typically is a rotating shaft supported by bearings over which a disc is attached concentric to the cross section of the shaft. That is, the center of the disc lies on the axis of the shaft, and the disc and the shaft as a single unit is called a rotor. Since the mechanisms of almost all machineries have some motion transmission from linear to rotary or vice versa, a rotating shaft or a rotor can be considered to be the heart of any machine system. These machineries, although fairly robust and well designed, shafts in operation are occasionally vulnerable to severe defects that develop without much apparent warning. Let's see the rotor or shaft defect. Defect due to misalignment. Here, the axes of the bearings or bushings which support the shaft are not collinear, meaning that the shaft is not in exact positional state as it is intended to be due to wrong fixturing or due to inconsistency in the bearing dimensions or position. uh, Rotor defect due to bow. Here, although the axes of the bearings are perfectly in alignment, the shaft itself is not perfectly straight throughout its length. There is some bending of the shaft somewhere along its length. Rotor defect due to mass unbalance. Here, the defect is due to non-uniform distribution of mass of either the shaft material or the disc material or both. This uneven distribution of mass in materials results in a little shift of the actual center of mass from the geometric center of the component, and this shift is called as eccentricity. Now, the defect due to crack, the most critical one. Here, the defect in rotor is due to presence of crack or cracks either in shaft or in the disc or in both. A crack is a small opening like slit cut on rotor surface which may occur due to poor manufacturing of the rotor material or which occurs during the operating period of the component. Crack detection or identification gives a qualitative indication about presence of some fault in the machine, while crack classification indicates whether that fault is a rotor crack. Crack localization provides information about the location of the crack, while the crack assessment provides information about shape and size of the crack. Crack prediction estimates the remaining useful life of the rotor. In the last 4 decades, extensive research work has happened into developing various problem-solving procedures to efficiently manage rotor cracks, resulting in numerous publications of technical papers on the topic. Therefore, a concise periodic summary of body of such work is very much needed. This paper hence does the review of the crack rotor literatures of the last decade, that is from the year 2010 to the year 2020 chronologically. Let's see. For the batch of 2010 to 2012 literatures, I'll pick a few from the listed literatures given. Karthikeyan and Tiwari in 2010 developed a flow algorithm for detection, localization, and sizing of flow in circular beam on force response measurement. Their flow model was in good agreement with their experimental results. However, they overestimated the flow size due to inherent low sensitivity owing to the beam being very thin and relatively long. Chana et al. In 2011 predicted the useful life of SPEI RB168MK101 engine rotor by propagating a crack and evaluated the ability of an eddy current sensor and a reasoner software system to isolate the crack. Kulitza and Sawicki proposed a rigid finite element method to model rotating machines wherein the crack was presented as a set of spring damping elements of variable stiffness connecting two sections of the shaft. Ricky and Penake developed a model of a real hyperstatic rotor with several degrees of freedom with the bearings and the system foundation and investigated system anisotropy and crack position. My comments on these chosen literatures in terms of scope for improvement. Karthikeyan and Tiwari, 2010, the proposed method could be tried with different end conditions like cantilever and with different flow model as well, which also considers the thickness of the flow along with its depth. Algorithm for smaller flows may be developed. For Chena et al. 2011, a greater understanding of different types of faults that might exist in a rotor assembly, and the ability to differentiate between them using the tip timing system is essential if the true nature of a fault is to be diagnosed and reported. For Kuleza and Sawicki, 2012, amplitudes of combination frequencies and induced coupled axial and torsional vibrations are very low, and these may be decently elevated for further study. Ricky and Penaki, 2012, results obtained by the present flow rate analysis cannot be assumed as valid for all rotating machines affected by transversal cracks. So here is the scope for further research. Now, a few more lists from the batch of 2013 to 2015. I'll choose a few of them from the listed literatures. Goa et al. Proposed a method for identification of early crack propagation in a Jeffcott rotor with a transverse breeding crack. Zafico-Vallée et al. Presented a model-based procedure for rotor crack localization and assessment to a small-sized test rig provided with a notch. They predicted both the position and the depth of the notch when the notch depth was greater than 20% of the rotor diameter and ascertained blind spots in the rotor. Haji and Oyadizi proposed a new approach based only on the orthogonal natural frequencies in both the horizontal and vertical lateral bending vibration planes for identification and location of cracks in non-rotating rotors. S.K. Singh and Teyi, 2015, investigated the behavior of a rotor bearing system with a breeding crack influenced by active magnetic bearing. Again, my remarks on the chosen literatures among the listed ones in terms of scope for improvement for further research. For Goa et al. 2013, noise is not taken into account. For small cracks, noise can have some influence on the decomposition process for superharmonic components by the EMD method. Therefore, in future work, the effect of noise on crack detection should be investigated. For Zapico-Vallée et al. In 2013, the procedure becomes unstable for lower values of notch depth. These results could be enhanced by using additional high modes and more accurate modal tests and modal identification algorithm. Haji and Oyadeli 2014. Using a roving disc with a mass ratio less than 8% of the shaft mass is not recommended. Use of a roving disc with mass ratio of more than 20.4% results in the danger of increasing the severity of the crack. Some research may be done here. For S. Singh and Tiwari, 2015, inclusion of the end support bearing stiffness for the multi-degree of freedom system with the finite element method may be taken up. Now let's go to the next batch of literatures, 2016 and 2018. Let us choose a few from the listed one. Gomez, Casajan, Corral et al. In 2016 studied vibration signals obtained from a rotating shaft under different crack depths and location. Goa et al. Experimentally investigated the dynamic behavior of a Jeffcott rotor and the AMD-based crack detection method. Wang et al. Presented the effects of unbalance on the nonlinear dynamics of the crack rotors by using the 3D finite element model and the contact approach to model the shaft and the reading crack respectively. Okay, so the comments. For Gomez, Castellan, Corral et al. 2016, it has applications in condition monitoring under stationary conditions only. Research can be undertaken for similar studies in dynamic system. Goa et al. More experiments for smaller cracks may be performed to find the minimum crack depth that can be detected experimentally by the proposed method, and how the initial crack width influences the dynamic behavior of the crack rotor system may also be studied. Wang et al. The method has issues with cracks with large depths because the dynamic response of a rotor with a deep crack is no longer much smaller than the static deflection. Some study may be undertaken in this regard. Now let us take the last batch of literatures from 2019 to 2020. Uh, She et al. Defined a new concept of instantaneous whirling speed of axis orbit studied by a Jeffcott rotor model. This new attribute significantly increased the effect of axis orbit for distinguishing normal and crack rotor systems. Hein and Januska in 2019 applied Haar-Wavelet discrete transform, uh, artificial neural network, and the random forest to predict the location and severity of a crack in an Euler-Bernoulli cantilever subjected to the transverse free vibration. Jiwen et al. Proposed a novel crack localization method based on Bayesian fusion of multi-scale superharmonic characteristic deflection shapes for stepped rotating rotors by extracting the crack-induced local distortion in the multi-scale superharmonic character deflection shapes. Again, my comments for them. For G et al. 2019, compound faults such as misalignment, oil whirl, or rubbing may lead to the confusion of instantaneous whirl characteristics, resulting in misdiagnosis of crack faults. In view of this, more types of diagnostic indicators should be studied to complement each other and improve the accuracy of crack diagnosis. Hen and Januska, a few other machine learning models may be trained for comparisons as they have taken only random forest classifier in their approach. Jiwen et al. 2020, the last literature of my survey. The method is limited for the crack rotors, thus the existence of cracks needs to be guaranteed by crack detection method before the application of the proposed crack localization method. And higher crack localization accuracy depends on more measurement points, hence advanced testing techniques such as distributed optical fiber sensing technology may be performed. Well, my last words. I have chosen 39 relevant literatures for this survey. The most common literatures, the most common journals were Journal of Sound and Vibration, Journal of Vibration and Control, Mechanism Machine Theory, Nonlinear Dynamics, and Shock and Vibration. Well, it is observed that the area of crack analysis is dynamic and continuously developing. A few authors are consistently upping their existing analysis by including newer techniques every year. Yes, a few authors like Lu Ziyuan, S.K. Singh, S. Singh, R. Tiwari, M.A. Al-Sudefat, A. Ibrahimi, J. Shi, and M.J. Gomez. These authors have most contributed in my survey, and they have come up with new publications with newer methodologies in short periods of time. Conventional FE modeling, amongst others, still is one of the most used modeling methods for numerical analysis and validation for experimentations. Artificial neural network is still chosen for data training. Various algorithms have been developed in the last decade, too many of them. While Jeffcott rotor model is still one of the favorites amongst the authors for crack rotor analysis. This paper is a sincere effort to provide a succinct guideline to the scholars in their initial stage of research in the area of crack analysis to choose proper objectives for their work, as the tables given provide scope for improvement of each chosen paper. Thank you. With these lines, I conclude my presentation. And these are the references, the 39 references. I have used search engine tools like Mendeley and Google Scholar to come down to these literatures. Thank you very much. My name is Nabam Teyi from Northeastern Regional Institute of Science and Technology, India. Thank you all.